Richard James arrived at the Philadelphia Naval Shipyard each morning in 1943, carrying the responsibility of solving a critical wartime problem. As a mechanical engineer, James faced the challenge of developing springs that could stabilize sensitive instruments on naval ships during rough seas. Radar systems, communication equipment, and navigation instruments all suffered when waves rocked vessels unpredictably, throwing delicate machinery out of alignment. The Navy needed a stabilization system that could keep these vital tools functioning regardless of sea conditions. James spent his days designing tension springs specifically engineered to absorb ship movement and protect sensitive naval equipment. These springs needed precise calibration to counteract the forces generated by ocean waves while maintaining enough stability to keep instruments level. The engineering requirements were demanding, as the springs had to respond instantly to unpredictable movements, while never overcorrecting in ways that might damage the equipment they were meant to protect. Each prototype required extensive testing and modification, with James running calculations for spring tension, metal composition, and coil geometry. The shipyard's engineering laboratory buzzed with activity as James and his colleagues worked developing prototypes. Tables throughout the facility held various spring designs, each representing a different approach to the stabilization problem. Some springs used thicker wire for greater strength, while others featured tighter coils for more responsive movement. James experimented with different metals, testing copper, steel, and specialized alloys to find the perfect combination of flexibility and durability. Late one November evening, James remained in the laboratory long after his colleagues had departed. He had been working for hours, surrounded by prototype springs and detailed engineering drawings. His latest design showed promise in preliminary tests, but fine-tuning the tension requirements demanded meticulous attention to detail. The overhead lights cast shadows across his workbench, which was cluttered with springs of various sizes, measuring instruments, and pages of calculations. Fatigue clouded his concentration as he reached across the bench to retrieve another prototype for testing. James accidentally bumped one of his tension springs with his elbow, sending the metal coil tumbling toward the floor. He expected the spring to simply drop and bounce like any piece of metal, then roll under his workbench where he would need to crawl to retrieve it. Instead, something extraordinary happened that defied his engineering expectations and understanding of basic physics. The spring seemed to come alive as it fell, moving in a way that James had never witnessed before in years of mechanical engineering. The spring landed on its end and immediately began what appeared to be walking. It moved from the workbench to a wooden crate, then stepped down to the floor with a rhythmic, measured pace. Each movement transferred energy through the coils in a mesmerizing wave pattern that continued for several seconds. The spring maintained perfect balance as it navigated obstacles, moving with an almost organic fluidity that seemed impossible for an inanimate metal object. James watched in amazement as the spring continued its journey across the laboratory floor, finally coming to rest near the far wall. James picked up the spring and examined it carefully, finding no damage or unusual characteristics that might explain its behavior. The metal coil looked identical to dozens of other prototypes scattered around his laboratory. He dropped it again, and the spring repeated its walking performance with the same fluid grace. James spent the next hour experimenting with different release angles and heights, discovering that the spring's movement remained consistent regardless of how he dropped it. The physics behind this behavior challenged everything he understood about tension springs and energy transfer. Unable to contain his excitement, James gathered several springs and rushed home to his wife Betty with claims about discovering something revolutionary. He burst through their front door carrying an armload of metal coils, breathlessly explaining that he had found the next great American toy. Betty James listened to her husband's enthusiastic description with natural skepticism, wondering how a pile of industrial springs could possibly interest children. Richard demonstrated the walking motion on their staircase, and Betty immediately understood the entertainment potential her husband had accidentally discovered. The couple spent weeks developing their spring into a marketable toy, experimenting with different wire gauges and coil tensions to optimize the walking effect. They named their creation the Slinky after Betty found the word in a dictionary, appreciating its definition of sleek and graceful movement. Richard calculated that each Slinky would cost approximately 75 cents to manufacture, allowing them to retail the toy for $1 while maintaining reasonable profit margins. They invested their savings into producing an initial batch of 400 units, confident that consumers would share their enthusiasm for the walking spring. Toy store owners throughout Philadelphia rejected the Slinky immediately, viewing it as worthless scrap metal with no obvious play value. Store managers examined the plain metal coils and questioned why children would want such a simple, industrial-looking object. The couple faced rejection after rejection as retailers explained that successful toys needed bright colors, moving parts, or obvious entertainment features. Many store owners suggested that the Jameses had fundamentally misunderstood the toy market and should abandon their spring project entirely. Determined to prove the Slinky's appeal, Richard and Betty arranged a demonstration at Gimbels department store in downtown Philadelphia during the 1945 Christmas shopping season. They set up a simple display featuring a wooden board positioned at an angle, allowing the Slinky to demonstrate its walking ability for passing shoppers. The couple had no experience with retail sales or toy marketing, relying entirely on the Slinky's natural appeal to attract customers. They arrived early on demonstration day with their 400 units, uncertain whether anyone would show interest in their unusual creation. The demonstration exceeded every expectation as crowds gathered to watch the Slinky's hypnotic movement. Children dragged their parents over to witness the walking spring, while adults stood mesmerized by the physics display. Within 90 minutes, all 400 units had sold completely, stunning both the Jameses and Gimbels management. Store employees had never witnessed such rapid sales for any toy, particularly one that appeared so simple and unassuming. The success proved that toys did not need elaborate features or flashy designs to capture public imagination. This simple metal coil has since sold millions of units over decades, proving that the most captivating toys often emerge from the most serious scientific work.